So do you guys have some idea of dynamic programming already before we even get started? Okay, some are saying no, some are saying yes. Great, but nevertheless, we'll be starting from the very scratch. So we'll be, dividing this entire series into sort of 7 lectures, and each lecture would be pretty long. Like I could have done it in a different way. Like I could have taken 30 minutes lectures each day, but I sort of like to, keep my schedule in this way that I take very big lectures in just one go. So all these 7 lectures that I'm talking about will be around 2 hours long. Some of them might be smaller than that, but mostly on an average they will be 2 hours long. So I would expect you to sort of stay engaged, although that's kind of my responsibility to keep you engaged. But just giving you a heads up that all of these lectures would be pretty long. So maybe you can grab some snacks along the way, and feel comfortable, and don't treat it like a normal lecture, like you have at your college. Can the meet be recorded and shared? Yeah. So the entire all these lectures will be recorded. First of all, we'll be sharing the links with you guys already, like just after the class. Also, I'll be uploading these recordings on my YouTube channel. So I think a lot of people here might know about my YouTube channel. In case you don't know about it, be sure to check it out. So yeah, I'll be also uploading the recordings on my YouTube channel. And one more thing, so I would sort of keep my video off. I've turned it on right now just so that I can give you an introduction and we can have like a very informal discussion. But in the lecture, I would like to keep it off so that I have my entire focus on the lecture and you guys also have your entire focus on the lecture itself. Right. So are we good to go? Are we good to start? Any questions anybody has? Okay, I'll turn off my video now. Fine. So let's get started. We'll be discussing about dynamic programming in these 7 lectures that are coming up. One important thing about dynamic programming is that this is kind of the most important topic when it comes to competitive programming. How am I saying this? Because I have been doing competitive programming for like the last 3 years now. And I know for a fact that almost 40% problems that I've solved till date were based on some dynamic programming idea. So if you want to get to a very good level in in competitive programming, DP would be kind of the most crucial topic, to prepare. So after these 7 lectures, you can, expect to solve any problem on code forces that is less than equal to 1900 rated, right? So I think that should be like a good enough motivation for you to attend all of these lectures. So we'll get started. This is day 1 of dynamic programming. And why do you need dynamic programming? We needed to, not solve the problems that we've already solved. So for example, if let's say I tell you that 2 plus 2 is equal to 4. Now, if let's say, somebody asks you 10 days later, what is 2 plus 2? Now, if you have to again calculate it, that is like a waste of resources, waste of time, right? You already know the answer, that it's 4. So dynamic programming helps us to keep track of already known answers. Basically, let's say we solve a problem, we store its answer somewhere. What does it help us with? Basically, if we require the answer ever again, we don't have to calculate it. We can just directly return the answer or basically tell them the answer. So a good enough problem could be to basically, find the sum of first, let's say, a million natural numbers. So although there exists a formula, but let's say you did not know about any such formula, what you can do is you can calculate its value and you can save it somewhere. So now if let's say somebody tells you to find out the, sum of first 1 million plus 1 natural numbers, what will you do? You will use the previous result that you had, right? So that's exactly where dynamic programming is used. We sort of tend to not repeat the problems that we've already solved. Fine. So let's talk about where exactly is DP used. So DP is used in a lot of different problems. There are 5 basic categories that I've listed here. Although in these 7 lectures, you'll realize that you can extend DP to even more topics. So the very first place where we require DP is the part of overlapping subproblems. So like I already told you, if you have the answer to a certain problem, you would not want to calculate it again, right? So if let's say your current problem and you want to solve it, let's say that problem is dependent on 3 other subproblems. Now, if you, let's say, know the answer to a particular subproblem, you would not want to calculate it again. That's exactly where DP is used. Where DP is also used in trying to maximize or minimize certain values. So let's say you get a competitive programming problem.
dirty lag raha hai.
Yeah. Let's say you get a competitive programming problem and the problem requires you to maximize or minimize certain value. So the very first idea that you can use is some sort of greedy algorithm. right? But dynamic programming basically helps you to find out this maximum or minimum value covering all possible cases. Basically, when we talk about greedy algorithms, we are sort of going into a particular direction. But when we talk about dynamic programming, we sort of tend to cover all the approaches and then come to a conclusion, right? So dynamic programming is also used to find out the number of ways to do a particular task. Basically, okay, you request live transcription. Should I enable that? I don't know. I'll just decline it for now. Okay. Yeah. So dynamic programming also helps you to find out the number of ways. For example, in your JE days, you would have solved these permutation combination problems. So dynamic programming also helps you to compute these answers computationally, basically not using some formula, but some code, right? So it helps you to find out the number of ways to do a particular task. And like I already said, DP versus greedy. When we talk about greedy, we are going into a particular direction. But when we talk about DP, we are trying to cover all possible cases, right? And DP is also used to solve problems where you have to check for a possibility. Let's say I give you a problem that you have a maze, okay? And you have to find you're standing at a particular point in a maze and you have to find your way outside the maze. So dynamic programming can help you, check for a possibility, whether there exists a path so that you can reach outside the grid or not. Dynamic programming helps you to find that as well, right? So is this clear to everyone? Will the slides be shared later? Yes, the slides will be shared as well. Can you tell the outcome of the lecture series in terms of CodeChef rating? In terms of CodeChef, I can say, although, when we talk about CodeChef, we don't really assign a rating to a problem, right? So if you're talking about easy, medium, difficult, then I can say after these 7 lectures, you'll be in a very good position to tackle medium level problems in TP. All right. Right. So now let's talk about this problem, which is, finding the nth Fibonacci number. How many people have already seen this problem? Finding the nth Fibonacci number. Okay, you've raised your hand. Don't raise your hand, just write a +1 in the chat or a -1. That would be better. Okay, great. So a lot of you have already seen it. Fine. What is the best time complexity in which you can find a Fibonacci number? This is like a general question, not something related to TP. What is the best time complexity that you know of in which you can find a Fibonacci number, like nth Fibonacci number? Okay, a lot of people are saying order of n. There also exists a method by which you can calculate the nth Fibonacci number in log n time, order of log n. So it's kind of based on the matrix exponentiation idea, although we're not going to discuss that right now. But after the class, you can check it out, like how can we find the nth Fibonacci number in log n time. So we don't use a particular formula. It's like a deterministic approach, not a non-deterministic approach, right? So let's talk about this problem of finding the nth Fibonacci number. A lot of you already know this, that you can find it in order of n. That's great. But let's say I tell you, let's try to find f of 6, basically. And I already have it in my slides. So if you have to find the 6th Fibonacci number, this is how your recursion tree would look like, right? If you have to do it naively, if you're not using dynamic programming, and if you're not using any clever ideas, this is the most naive way to do it. So would you all agree with me on this? This is like the most naive way to find the nth Fibonacci number, right? So if you have to find Fibonacci of 6, like 6th Fibonacci number, it depends on what? Look at this formula. You have f of n is equal to f of n minus 1 plus f of n minus 2. So f of 6 will be what? F of 5 plus f of 4. Now, in order to calculate f of 5, you have to again, find f of 4 and f of 3. And similarly, like the tree goes down and down. Basically, if you have a problem like finding f of, let's say, 100. So can you imagine how far the tree will go? Like it will continue to go down. This will be like a very long tree if you have to find f of 100. Right. So if you do it naively, can somebody tell me the time complexity of finding the nth Fibonacci number? Like if we were to use this approach, this recursion approach, the time complexity to find the nth Fibonacci number. Two to the power n. Yeah, that's like a good estimate. A better estimate is like actually some golden ratio to the power n. Like when you talk about this recursion tree, the actual time complexity is some golden ratio to the power n, but 2 to the power n is like a very good estimate. How are we saying that? Also, like I would want you to sort of turn off your video. Yeah, cool. So how am I saying that? The complexity is 2 to the power n. What is the intuition behind it? If you look at any node in this tree, can you see that any node in this tree is dependent on two children? Basically, if you have to find f of 4, it's dependent on f of 3 and f of 2. So every node in this tree is kind of dependent on two other nodes, right? So you have n nodes, and for every node, you have a possibility of 2. So it's like 2 to the power n. But it obviously, is like making sense that like f of 2 will not be dependent on two children. F of 1 will not be dependent on two children. So it's not like all of the nodes are dependent on two children, but most of them are. So 2 to the power n is like a good estimate for the time complexity of this. But can you see something in this problem? Can you see that if, let's say, we were finding f of 6, and let's say we found, we said that f of 6 is dependent on f of 5 and f of 4. What is happening? We are calculating f of 4 twice here. Like when we were finding f of 5, it was dependent on f of 4 and f of 3. So to find f of 5, we are first of all calculating f of 4. But in order to calculate f of 6 as well, we are finding f of 4. So can you see that there are some overlapping subproblems here? Is this making sense to everyone? That we have some overlapping subproblems? Great. Okay, tell me any other overlapping subproblem here. Like I already showed you that f of 4 is an overlapping subproblem. We are calculating it again and again. Give me another subproblem that is overlapping here. What do you think? F of 3, right? Look at this. Let me just get some laser here. Yeah. Look at this f of 3. This f of 3, we are finding it here first. Then we are finding it here again. And then we are finding it here again. Should we do this? Like, should we find f of 3 again and again? Or should we just find it once and then, compute the answer? Just return it every time we need it. What do you guys think? Should we find it again and again? Okay, I don't see any answers here. What do you guys think? Should we find f of 3 again and again, or should we like store it? Find it once and then store it, right? Cool. So now I see some responses. We should find it once and we should just store it, right? So now let's talk about this concept of memoization. Okay. And this is exactly what you guys have told me. This is not something that I have told you. When we were finding f of 6, when we were finding f of 6, you said that we have f of 5 and f of 4. Okay. And then after this, we have this f of 4 and f of 3. And for f of 4, we have f of 3 and f of 2. Okay. Now you guys told me that, when we let's say found out f of 4, let's say this value is already found. What should we do? We should store it somewhere. Where can we store it? We should store it in a place which is like quickly accessible. We don't have to take a lot of time to access that memory. And then whenever we require this value, we can directly return it. Right? Is this making sense to everyone? When we found out f of 4 here, let's say we were going on this path first. We found f of 4 here. Now when we reach here, we already have the value. So we should not calculate it again. Right? So what should we do? What do you think are the two requirements here? The first requirement is very simple. You need to check if some f of x is already found or not, like if it has been calculated or not. That's like a valid problem, right? When we are finding f of 4, we first of all need to check whether f of 4 has been previously calculated or not. If it has been previously calculated, we will not calculate it. If it hasn't been calculated, we will calculate it, right? So the very first thing that we need to make sure is that have a way so that we can decide whether f of x has been calculated or not. Okay. So that's the idea. Like why should we calculate f of x again and again? And once we found f of x, we should store it somewhere so that the next time we need it, we can directly return it. Fine. So this is our condition for memoization. Memoization is like some sort of caching. You're finding some answers and then storing them somewhere, right? So our main task here in memoization is this. We first of all need to check whether f of x has been calculated or not. If let's say we have a mechanism to do this, then what are the two conditions? The first condition is that it hasn't been calculated before. If not, then calculate it and store it. If yes, then directly return the value without calculating. Is this slide making sense to everyone? This concept of memoization? Okay, perfect. Now tell me this. We have this, right? F of 6, or let's just look at this page itself. We have f of 6. What is the, we need to design a mechanism, right, to check whether some f of x has been calculated or not. So can you guys first of all see that if I have, let's say, an array, let's say I have an array going from index 1, we're considering 1-based indexing here, going from index 1 to n, what I can do is I can, mark them as Boolean. Like we can have a Boolean array. And initially, all of them are false. Right? So what is this Boolean array helping me to do? This is helping me to track whether some f of x has been calculated or not. Initially, all of them are false. Now, let's say, in our program, somewhere we found f of 4. This is 2, this is 3, this is 4. Let's say we found out this value, and let's say this value is some sort of number. Let's say it is 10. What should I do? Should I update this array as true? Should I not make it true? Because now we found out the value. I can do this, right? I can have a Boolean array which stores false everywhere, which states that none of these values has been calculated. Whenever we are finding some value, we'll mark it as a true. So now let's say somebody comes up and tells me, somebody comes and asks me what is f of 4. How do I get this value 10? I look up inside this array. This array tells me that this value hasn't been calculated before. So it must be present somewhere, right? So what we can do is we can create another array. And in that array, initially, it doesn't really matter what we are storing, because in order to even look up in this second array, we first of all look up in the first array. And we check whether the value is true or not. So when we are finding f of 4, there are two tasks. First of all, we change this false to true. Okay. Yeah. We change this false to true. And then in the second array, we also update the value, which is 10. So can you now see that if we have two arrays, I can easily, I can easily find out whether some value has been calculated before or not. And if it has been calculated, I don't need to calculate it again, and I return that value. Is this making sense to everyone? Like keeping two arrays, and one of them is the value array. The other one is to check whether some value has been calculated or not. Okay, perfect. Now my question to you guys is that can you convert this two array approach into just one? Do you need two arrays, or can you do it with just one array, saving some space? We can use one array. What we can do is that we can have a single array, and this array contains the values. Okay, it contains the actual values. Now understand this. Can you see that if you look at Fibonacci numbers, we have this addition of numbers, right? And the first two numbers are 1. So if we add numbers, we will always get a positive number, right? We have 1. This is how your Fibonacci numbers will look like, right? 1, 1, then 2, then 3, then 5. So all of these numbers are positive. What can I do? Can I just store a zero at every index? 0 tells me whether that value has been calculated or not. And if it is a non-zero, then that means the value has been calculated before. Can I do this? Can you repeat, please? I'm not able to understand. What exactly do you want me to repeat? Like this concept of memoization. Okay, so I'll just go on for now. Memoization is nothing, basically, like I told you. If you have this Fibonacci, if you have this recursive tree, we're calculating the same values again and again. If we have f of 5, look at f of 5. F of 5 is dependent on f of 4 and f of 3. So we are finding this f of 4, but look at this f of 6. This is also dependent on f of 4. So we are finding f of 4 twice. So instead of finding it twice, just find it once and store it somewhere. That's memoization. Now we discussed this approach of using two arrays. One array is to signify whether that whether that value has been calculated or not. The second array is to look up when the value has been calculated. All right. So what we were doing was we were converting these two arrays to just one. And our observation was that all of these Fibonacci numbers are greater than what? greater than 0. So clearly I can just have a 0 value at every array index, and that will tell me whether the value has been calculated or not. So let's say I do this and this value hasn't been calculated, this hasn't been calculated. Let's say I get to f of 5. This is f of 5, right? Let's say somebody tells me that f of 5 is what? F of 5 is 5. What do? You go to the fifth index and you update the value from 0 to 5. Now, every time somebody comes up to you and asks you f of 5, you look up in this array and tell them if the value is 0, you calculate it. If it is non-zero, you return the value. So is this concept clear to everyone of memoization? Okay, perfect. Now, what do you get out of this one slide? If I were to give you any general DP, some general memoization, not Fibonacci numbers, can you always do it with two arrays? Can you always do this memoization thing with two arrays? Tell me this. You can always do it with two arrays, but when can you do it with one array? What is the observation that you need to have to do it with one array? There should be some value x, which can never be attained by any of these what do you say, any of these indices. You should have a value x which can never be attained by any of these indices, and you can put x there. So a lot of people who have been doing DP for some time know that generally we put x equals to -1, because generally the answers are positive, they're not negative. So generally we put them as -1. But now you get the idea why we put -1, right? So this is what I have in terms of memoization. And let me just quickly compare, these two approaches. Like obviously the time complexity is much better. We haven't really discussed that right now. But let me give you a practical, example of it. Like how are we even saving operations here? So look at this. Without DP, this would be your normal recursive function, right? Spend like 10-20 seconds understanding the slide, if this makes sense to you. Basically, helper n is nothing but Fibonacci number of n. I mean, f of n. So how do you find f of n? There are two base cases. If n is equal to 1 or n is equal to 2, you return 1 in that case. And that was here on this slide, f of 2 and f of 1 being 1. And other than that, you always return the summation of the two children. Is this function clear to everyone? Now, I have specifically used the parameter, which is what? Which is function entered. This function entered, okay, just a minute. Yeah. This function entered tells me how many times have I entered this helper function. So can you see that this value is pretty large here? And also, is this making sense that the number of times you enter the function, that would be roughly the number of operations that you're doing? Is this clear to you guys? Yeah, this number is huge, right? Now let's convert this recursive idea into memoization. Let's memoize stuff. And what you'll see is this. We had this value called -1. -1 signifies that this particular value hasn't been calculated. So what are we doing here? Let me pick up a laser here. What are we doing here? We are checking whether the value has been calculated before or not. If it has been calculated before, you return that value directly. You don't have to calculate it again. But if it hasn't been calculated before, what do? You find the value here, dp of n is equal to helper of n-1 plus helper of n-2, and you return that value. So is this concept making sense? Like what have we done here in terms of memoization? Without calling, I mean, we're not calling the function every time now. We are only calling it when a particular value hasn't been calculated before. So now can you see the number of times the function has been entered? Is this number small or is this large? This is pretty small, right? Now, like just compare these two slides and you'll understand how we've converted this recursive idea to some memoization idea, and we've saved time and as well as operations, computational operations. So this was like really huge, this number. And then we got to just 57. So is the idea of memoization clear, and is the motivation behind doing it clear as well? Somebody's asking, can you explain how memoization is working in this? I'm not really sure what you mean by that. Like, do you want me to explain memoization entirely again? Okay, so let's do one thing. The thing is that we'll have a recording of this entire session. So what you can do is you can watch the recording, right? I think we've covered this entire concept 2 times, so it would make sense to now look at the recording. Fine. So now let's move ahead and let's solve another problem. So spend around 20 seconds reading this problem. So you have a grid of n cross m. Here n is equal to 3 and m is also equal to 3. And you have to start from the top left and go to the bottom right. Okay. You have to choose a path such that the value is minimized. Okay, before we talk about the solution to this problem, uh, tell me this. What have we already studied till now? Have we studied this concept, overlapping subproblems? And what did we use to avoid this overlapping subproblems thing? The idea is memoization, right? Now we are sort of trying to do this thing. We are trying to minimize or maximize some value, right? But again, here as well, we will be using the concept of memoization itself. Memoization will be used in all of these concepts, all of these ideas. But this is like the second type of problem that you can solve with TP, right? So yeah, give me a naive way to solve this, a brute force way. Okay, somebody saying minimum from left and minimum from right. Not left and right, but down and okay. One more thing. When I say you have to find the minimum, some path you can only go down and you can only go right. Okay, you cannot take any random path. You can only go down. Sorry, you can only go down or you can only go right at every point. Okay. We will calculate the sum along the paths and return the minimum. Yeah, that's one approach. That's like a brute force approach. Anything else in your mind? How do you solve this problem? Naively, not using DP, but naively, in a brute force way. Recursive function. Okay, good. Yeah, recursive function should do. What you can do is this. Just a minute. Yeah. What you can do is this. You have a grid here. If you are standing at any point, how many choices do you have? First of all, tell me this. If you are standing at any point, how many choices do you have in order to reach the bottom right? You have just two choices. You can either go here or you can go here. So at every point, you have two choices. So let's say I define my function as f of ij. And what f of ij tells me is minimum some path. Sorry, don't mind. I mean, my handwriting would be really bad here. So minimum some path from ij to n minus 1 comma m minus 1. Can I define a function like this, f of ij? What do you think will happen in this function? So you have this grid and you're standing at a point. Okay. And you want to find f of ij for this point. How do you find it? What you can do is like, obviously this is a recursive function. So first of all, you can call another function here, which will be what? F of I comma j plus 1. And another function you can call here, which would be what? F of I plus 1 comma j. Right? These are the only two choices you have. So f of ij will be what? First of all, you'll add this value. What is this value? This value could be something like a of ij. You will add a of ij plus you will take the minimum of these two. You would obviously want to minimize the sum path, right? So you would want to take the minimum of these two. What you'll say is give me the minimum of f of I comma j plus 1 comma f of I plus 1 comma j. This will be what? F of ij. Is this making sense to everyone? What have we done here? Okay, now tell me this. If I am doing like a normal, recursive approach, what would be the time complexity of this? Like doing something like this. You are standing at a point, call both of these functions without caring about whether some value has been calculated or not. You go here and you go here. So at every grid cell, you have two choices, right? So what do you think will be the time complexity of this? Two to the power n, not two to the power n, but you have like n into m cells, right? You have n into m cells. And at every cell, you have a possibility, like you have two possibilities. So the time complexity would be like roughly 2 to the power n, n into m. But does somebody have a better estimate for this? Not 2 to the power nm, but something better. Okay. Before we discuss that, tell me what will be the time complexity if you have just a single line. You don't have an entire, what do you say, grid, but you have a single line and you can only move here. And let's say these are m cells. N is equal to 1. So according to the time complexity that we have decided right now, the time complexity would be what? 1 times m. But is that the right estimate for this type of an example? When you can only move just one in one direction. It is not right, right? So the better estimate is a combination of n plus m minus 1 comma m minus 1. What is this term? Like if you look at this grid, have you guys studied this concept in your JEE time that, if you're standing here in a grid and if you have to go here, let's say you have to make n uh, and down directions, like you have to travel n times down and you have to travel m times what? You have to travel m times right. So what happens here? Like how many ways are there to do this? Basically, you have to travel n times down and m times right. But you can rearrange these characters however you like. You basically have a string like D, D, R, D, R. You have the string. And you have to find out the number of combinations number of permutations of the string basically. So what is the answer for that? Yeah, it's n plus m divided by n factorial m factorial, right? So, but how many down operations do you have to make here? You have to make n minus 1 down operations. And how many right directions do you have to make? You have to make m minus 1. So adding these, you will get n plus m minus 2 divided by n minus 1 factorial and m minus 1 factorial. I think this should be like not, I think I've written this wrong. So let me just update it here. This should be n plus m minus 2. Fine. So is this not same as combination of n plus m minus 2? You have this. This is same, right? So the actual time complexity is this value. But this is also kind of exponential only. You can assume it to be exponential, right? So the time complexity that you might think of could be 2 to the power mn, but I've given you a case where this is not exactly 2 to the power mn, but the actual time complexity is this. Okay, so is this clear to everyone, the naive way to solve this problem? Okay, so now let's talk about the efficient way, which is using memoization. So tell me one thing, let's say you have this grid. Let's say you have a cell here. So give me a yes or no in the chat if you feel that this cell, the answer of this cell would be dependent on the answer of this cell. What do you think? Will it be dependent on the cell? Yes, it will be dependent. What about this cell? Okay, somebody's saying no. When you're saying no, what I mean, I don't mean directly dependent, but I mean indirectly dependent as well. Basically, you have a path, right? You will be going like this. So this would be one of the paths. So it does depend on this as well. Now tell me one thing. This was cell 1, this was cell 2, and this is, let's say, cell 3. Do you think the answer of cell 3 will depend on the answer of cell 2? Why no? It will depend again. See, from cell 3 also you can take some path and reach this cell, right? So as long as you can reach from cell 3 to cell 2, you can, it is dependent. So tell me one thing. When you are trying to find the answer of this cell, you will be requiring the answer of this cell, right? Not from 2 to 3. Did I say 2 to 3 in my previous question? Oh, sorry. That's my mistake. Sorry. So the answer of 2 is not dependent on the answer of 3, but the answer of 3 is dependent on the answer of 2, right? Yeah. So tell me one thing. If I am finding the answer of 1 and I'm saying that it is dependent on 2, and let's say when I'm finding the answer of 1, I am also calculating this. So while I am finding the answer of 3, should I calculate the answer of 2 again? Or should I store it somewhere so that I don't calculate it? We should store it. So that's again memoization. What we can do is this. Let me just open Sublime Text maybe. Yeah. Also, let me just check if I have the code already available. No, I don't have it. So let me just code it up for you, and I'll just tell you exactly how this is happening. So this is some code that I have from some other class, but yeah. And I'm using C++ right now, but this is like I will not be using some C++ specific stuff. Okay. So let's say I have a grid. This is my grid here, n cross m, right? And I have that function, like I said, int f of, this is the place where I'm standing right now. Okay. So what do you have to do? You have to just return f of 0, 0. What does this mean? I am starting from 0, 0, and I want to reach n minus 1, m minus 1. And I want to path that, is there for me. So let's increase this. Yeah. Okay. What do you think is the base case? Like, first of all, we can get outside the grid as well, right? If we are standing at a point, we could make a direction in which we move outside the grid. So what happens in that case? Let's say if I is greater than equal to n, or j is greater than equal to m. In this case, I can return some very large value, infinity. We are trying to minimize our answer, remember? So if we get to a possibility where we are exploring a non-explorable path, we should return infinity in that case. What is another base case? Another base case could be that if we reach the end. In this case, what do I return? I return the value present there. Okay. And then we have two possibilities. We return a of ij plus minimum of f of I comma j plus 1 and f of I plus 1 comma j. So is this code making sense to everyone? This is without the memoization. Right now we've written a very naive recursive code. Okay, so people are talking about what is this entire code that I have. Don't look at it. This is not something that we're going to cover today. So this is the code, actual code. Yeah. So is this part making sense to everyone? This is without the memoization. Okay, now what do we do when we want to memoize it? Think about it. A is the input. Sorry, so this is grid. Yeah. Grid is like the grid that has been given to us. We are not taking the input here, but yeah. Store in some matrix. So what we can do is we can have another DP matrix n comma m. Okay. But what do you think we should store, as that value x? Do you guys remember this? I told you this, right? That when you are creating a DP array, you have to have a value x which is unattainable in any case. What do you put as x now? Let's say I tell you that all the values in the matrix are positive. Now what do you put as x? You can put x as 0 as well. You can put x as minus 1 as well. Or you can put x as minus infinity as well. Right? I mean, anything that comes to your mind. So assume every value here is what? Here is minus 1. So how do I check for memoization now? You guys remember that first of all, even before I calculate my answer, I have to check it. So I'll say if dp of ij is not equal to -1. This means this state has calculated before, right? What do I do here? I just simply return dp of I comma j. And otherwise, what do? I calculate it and then I return that value. Instead of writing it like this, for people who are getting confused, I can even write it like this. Okay, now is this clear to everyone, this code? This is the part where we check whether the state or the sub problem that we are solving has been solved before or not. If it hasn't been solved before, what do? I solve it. And if it has been solved before, I return it directly. I don't calculate it again. Okay. So right now, you guys must have seen that we are not really talking about the time and space complexity. So we'll come to that, don't worry. But right now, understand that we are moving from some inefficient programs to some efficient programs. In the second, if you have written sorry, I cannot understand what you've written here. I am sorry, can you explain that part, why the answer of cell 3 is dependent on the answer of cell 2? Oh, right, sure. So what I was saying was this. It is kind of, in the way we've defined a problem. How have we defined a problem? We are standing on some cell I comma j. And we are saying that the answer of this I comma j is what? It is the minimum sum path from ij to n minus 1 comma. I have to find the minimum sum path from this point to the end to this point. I will be also exploring this path. I'm trying to explore all the paths, but I want to find out the minimum sum path. So when I'm standing on 1, I can say that my answer is dependent on 2, the answer of 2. And similarly, if I'm standing on 3, then also I would want to explore this path. Okay, somebody saying you've written, okay, right, this should be grid, but you guys get the idea. Like A and grid are basically the same thing that I had written till now. Grid is the input matrix. This case is moving outside the grid, not allowed. This is reached the destination. This is what I have. So is this clear now, this entire code? And also, can you see that this is much more efficient than the previous approach? For any cell, look at any cell now, we calculated just once. We calculated just once, right? We never calculate the same cell again. So what do you think will be the time complexity of this? Any general guesses? Although we haven't really discussed how to find the time complexity, but what do you think? If you look at this entire matrix, in this entire matrix, we are finding the answer for every cell just once. Just once. And how are we finding the answer for a cell? We are finding the answer of a cell by doing this. We are finding it just once. So there are n into m cells. And for every cell, if I can get my answer in order of 1, I am getting the answer in order of 1 if I assume that this part has been calculated before. Like there should be a semicolon here, but yeah. If I assume that this part is solved already, can I say that finding dp of ij is nothing but an order of 1 task? Right? So that's exactly how you, like, we haven't really again discussed how to estimate the time and space complexity, but you should get the idea now that for every cell, I am finding the answer just once. So what do you think would be the time complexity? I mean, the time complexity here is n into m. But for the Fibonacci problem, we had this Fibonacci problem, right? Here, what do you think is the time complexity of this approach? Again, for every state or for every element or for every index, we are finding the answer just once. So what do you think is the time complexity of this approach, this Fibonacci program? It is order of n, right? Cool. Okay, tell me one more thing. What do you think is the space complexity of this entire code? What are we doing? We are creating just an extra 2D, sorry. Okay, I thought somebody wanted to speak anything, but yeah. So can you see that in this problem we are just creating one extra array, one 2D array, and then that is like n into m of dimensions n into m, and we aren't creating any other extra memory anywhere. Are we creating some extra memory? I mean, anywhere else? This is like a recursive code, so let's not like take into account the the space complexity of this call stack here. So the space complexity of this is order of n into m. But what about this one? What is the space complexity of this DP? I mean, this Fibonacci problem that we have solved using memoization? Order of n, right? Cool. So you guys get the idea of these two problems, the Fibonacci problem and this problem of finding the minimum sum path from top left to bottom right. Right. So let's wait for like 1 minute to address any questions that you have. Right. So you guys are free to write in the chat as well or unmute as well. Okay, so no doubts. Should we move ahead? How to figure the recursive condition? How to figure out the recursive condition? You tell me, what do you think? This is very simple. You define a subproblem. The very first task is to do what you have to do is to define a subproblem. And then when you have a subproblem, you just try out all the possible ways. Okay, somebody is saying how to figure out the recursive condition, like there we had minimum of 2 grids. So I think this is like kind of really elementary. If you don't have idea about recursion, you should read about recursion first. But if you have the idea of recursion, then defining that recursive condition is nothing but first of all finding a subproblem. What are you trying to solve? And then representing this subproblem or trying to find out the answer for this subproblem using some other, by calling some recursive function again. Having an equation basically. Like look at this code. You have an equation, right? To find out the answer of your subproblem, you have an equation. So first of all, you defined your subproblem. What is the subproblem? F of ij represents minimum sum path from I comma j to n minus 1 comma n minus 1. This is your subproblem. Now, how do you find out the answer for that subproblem? You define an equation. So we'll be talking about these two concepts of state and transition. Don't worry about that. This should make things a lot clearer, right? So any other doubts, or should we move ahead? Okay, let's move ahead now. So let's talk about these two concepts. One of them is state and the other is transition. So since we've already solved two problems, made a lot of sense. But now looking at these two problems, we can, make some sense out of these two. What do you say? Two terms. Okay. So give me a minute. Yeah. So the first concept is state. And a state is nothing but a subproblem. So I have this definition here, which is like kind of a little formal. A state is nothing but a subproblem that you want to solve. The subproblem can be easy or complex to solve, but the final aim is to represent the final problem that we have by a relation between these subproblems, right? If it is not making sense, look at this example. So for this problem, when we had this grid problem, we had to go from what? We had to go from the top left to the bottom right. So what is our final subproblem? Think about this. What are we trying to do? We're trying to find out the minimum sum path from the top left to the bottom right. And how did I define my subproblem? I define my subproblem as this, that instead of trying to find the answer for this directly, first of all, define another subproblem, which would be standing at any point I comma j, find out the minimum sum path from that to n minus 1 comma m minus 1. So can you see how this is a subproblem? Okay, before that, first of all, tell me if this is problem 1 and this is problem 2. This is like you are standing at the top left, this is problem 1, and you are standing at this I comma j, and this is problem 2, which is easier to solve, like which would take lesser time to get solved. Finding out the minimum path in this grid or finding out the minimum path in this bigger grid, which is easier to solve, problem 1 or problem 2? You have this. Problem 1 starts from here. You want to find out the minimum sum path in this entire grid, and the second problem is that you have to find the minimum sum path from this cell, which is easier to solve. The second problem is easier to solve because like it is very obvious. The grid here is smaller, so you have lesser possibilities to try. So can I say that this is a subproblem? That this 2 is a subproblem of my bigger problem? Right? So that's exactly what a state means. You have a subproblem and you need some parameters to define it. First of all, this is a subproblem. Okay, is this a subproblem? Starting from this cell 3, is this also a subproblem? Okay, is this also a subproblem? Starting from this cell 4. All of these are subproblems. But now the question is, how do you differentiate between these subproblems? How do I say that this is a subproblem, let's say A, and this is a subproblem B, and A and B are not same? How do I differentiate between them? That's the question. And the answer to this is by using some sort of parameter. So if you look at this approach, I told you that you have f of ij. You have this f of ij. And sorry, what does f of ij represent? F of ij represents the minimum sum path from a cell I comma j. So can I say that this is my state? I have a subproblem. I have this subproblem. I have this subproblem. I have this subproblem, and now I can differentiate between them. Can you differentiate between this subproblem and this subproblem with this f of ij, like these two parameters I comma j? So that's the entire concept. First of all, you have a bigger problem. You break it down into smaller problems, and we call these smaller problems as subproblems. Now, the second task is to differentiate between these subproblems. How do you do that? By having some parameters. What are the parameters here? Anybody in the chat? What are the parameters here that we are using to differentiate between any two states, any two subproblems? I and j. Right? So that is exactly what is meant by a state. So any doubts in this concept of a state? This is like a formal term. Whenever I will be discussing a problem of DP from this point, I will be always telling you that this is the state, this is the transition, this is the final subproblem. So knowing what a state is very important. So is the concept clear to everyone? What is a state? You have a problem, you break it down into subproblems, then every subproblem needs some parameters to define it so that we can differentiate between two subproblems. Right? Now let's talk about this concept of transition. So can you see that when I said, f of ij, I had this equation. I have f of ij, and I have this equation, which is what? It is nothing but equal to a of ij. A is like the input matrix that has been given to me, plus minimum of, you have two possibilities here, f of I comma j plus 1 and f of I plus 1 comma j. So what do you think is this equation? What are we doing in this equation? In this equation, we are trying to find out the value of f of ij using the values of f of I comma j plus 1 and f of I plus 1 comma j. Right? So isn't this like an equation? If I assume that this has been calculated already, if I assume that I call a recursive function and it returns me the actual result, the correct value, and I again call a recursive function which returns this value, which is a correct value, then can I say that this equation is valid? This equation. And this equation is nothing but a transition. This is called a transition. Defining an equation or defining a relation by which you can calculate the answer of every single state in your entire pool of subproblems, that is called a transition. Will this equation solve the answer for will this equation solve it for every cell in the grid? If I have a grid and I define this equation, f of ij is equal to a of ij plus minimum of these two possibilities, will it solve for every cell? It will, right? So that is exactly a transition. Defining a relation by which you can calculate, defining a relation by which you can calculate the answer of unknown states by using the answer of known states. So what is the assumption that I have? The assumption is that this f of ij will give me the right, this f of I comma j plus 1 will give me the right result. It will not give me a faulty result. This is the assumption that I have. Similarly, for this function, I have the assumption that this will give me the right result. Now, if I have the answers of these two, I can calculate an unknown value, which is f of ij. So is this correct? And is this clear to everyone? Like what is the state and what is the transition? Okay. Now let's have an exercise. Let's try to, talk about the state and transition in the Fibonacci problem. And I'll just update it as well. And when I share the slides, I will, share the updated slides. So yeah, what do you think will be the state in the Fibonacci problem? This was our problem. This is the code. So what do you think is the state? Okay. Remember, we have this entire array. And what is our main problem? We have to find this f of n. This is our final problem. How are we finding f of n? Yeah, exactly. Our state is nothing but dp of I. dp of I, or we can also say it is f of I. That is our state. But what does the state mean? What is the meaning of the state? You also have to tell me the meaning of the state. F of I or dp of I. What is the meaning? When I say dp of I or when I say f of I, what is the meaning of the state? It is Fibonacci of I, right? So whenever, in these all 7 lectures that I'm going to conduct, this is one thing that you always have to remember now, that whenever I ask you for a state, don't just tell me some random stuff like dp of ij. I don't know what is dp of ij. You have to clearly define what is the meaning of dp of ij, right? I've seen this with a lot of people, like whenever they're preparing for interviews, they try to memorize all these states. But the point is that if you don't understand what is the meaning of a state, then it's useless, right? Like if you have a cache memory and you don't tell me what is the use of that cache memory, having it is of no good, right? So whenever you define a state starting from this point, always tell me what is the meaning of that state. So the state in this problem, the Fibonacci problem, is we have dp of I, sorry, or f of I, meaning ith. Okay, what is the spelling of Fibonacci? Correct. So is this clear? dp of I or f of I meaning ith Fibonacci number. Is the state clear to everyone? Okay, now tell me what is the transition? What is dp of I equal to? You have to have a relation which gives me the answer for any general I. What do you think is this? Look at this code again. Fibonacci of n is dependent on Fibonacci of n minus 1 and Fibonacci of n minus 2. So once you know this, you already have the transition, you have a relation. So this will be dp of I minus 1 plus dp of I minus 2. Is this entire thing clear? The concept of a state and transition with respect to the Fibonacci problem. Okay, let's have another exercise. Let's talk about the state and transition in the matrix problem. Give me a state and give me a transition for this. First of all, give me a state now. What do you think should be the state? And remember what I told you. Don't give me some random f of ij. I don't understand what f of ij means. I mean, what is the significance of f of ij? When you write f of ij, tell me what it means, exactly what it means. So somebody is saying state is the shortest path to point ij. Or basically you can say, okay, somebody has also written dp of ij is the shortest path from, I mean, that's not how we defined it. So Varun, you've written dp of ij is equal to shortest path from 0, 0 to I, j. But remember, how are we solving this problem? There are two ways to solve this problem. Either you can solve this problem assuming that f of ij is the shortest sum path from 0, 0 to this cell, or you can say that it is the shortest sum path from I, j to n minus 1, m minus 1. So we were assuming that this is the case because this is what we have discussed till now. Shortest sum path from I, j till n minus 1, m minus 1. Good. So we have dp of ij is equal to shortest sum path, sorry, from I, j to n minus 1, m minus 1. So this is the state that I have. What is the transition? dp of ij is equal to what? Think about the relation that we found out. What do you think is the transition? Give me an equation for this. Somebody is saying grid of ij plus minimum of, yes, that's right. So I'll say grid of ij plus minimum of dp of I plus 1. This is like going down. And another is dp of I, j plus 1, which signifies going right. Cool. So I think now dp of I mean, the transition and the state concept should be clear to everyone. What do we mean by state and what do we mean by transition? Cool. So now let's try to solve another problem. Okay. How many more slides do I have? Yeah, this is fine. So let's solve another problem. This is the problem that you have now. Is the question clear to everyone? And is the example also clear? Like what is happening here? This is the array that has been given to you. One of the ways of choosing elements from, I mean, you have an array, you want to choose a sequence or a subsequence of elements from this array such that the picked up elements are never adjacent and you're trying to maximize the sum of total, I mean, the sum of picked elements. So if you look at the first example, when we pick up 4 and 10, we get a sum of 14. So tell me one thing, can I pick up, can I pick up 4, 10, and 5? Can I pick these three elements up? Okay, so the question is not clear. The question is this. You have an array. You want to pick a subsequence out of this array. Let's say you have some element. You want to choose some subsequence. Let's say you pick up this element, then you pick up this element, and you pick up this element. The element that you picked up should never be adjacent. So can you see that this element is not adjacent to this element? Similarly, this element is not adjacent to this element. But if I pick up another element, this one, these two will become adjacent. So our condition is that you want to pick up elements such that they're not adjacent, but the sum of the elements that we picked up is maximized. All right. So I hope the example is clear. Like the first one is giving you a sum of 14 and the second one is giving you a sum of 13. Both of them are valid subsequences. But a sum of 14 would be a better choice, right? Okay. So what is the, what is the thing, what is happening here? Which problem are we solving here? Look at this. Obviously, we have some overlapping subproblems in this. We are not discussing that. But what are we trying to do? Are we trying to find the number of ways? Or are we trying to do some greedy? Or are we trying to check for possibility? Or are we trying to maximize or minimize some value? We're trying to maximize the sum. Also, one more thing, like somebody saying dynamic programming instead of greedy. We haven't really talked about that right now. But obviously, since this is a class on dynamic programming, you guys get the idea that this problem will be solvable using dynamic programming. And this would be like a homework for you. You have to tell me why can't you solve this problem that I just showed you guys with a greedy approach. This would be homework for you, okay? But since this class is on dynamic programming, I'm not going to really discuss why we are picking up a why we are picking up a DP approach and not a greedy approach. Okay. So we have this Discord server, and I think you guys can let me know why do you think like a greedy approach will not work here. Fine. So now let's talk about the terms that we've discussed. You have an array. So give me a state. Okay, first of all, tell me this. The final subproblem that we're trying to solve is this, right? We want to go from this end. I mean, you can solve it in two ways. You can go from left end to the right end, picking up some elements, or you can go from the right end to the left end, picking up some elements, following this condition that the elements that you're picking up are never adjacent. So can you see that if we are picking up, let's say this approach, that going from left to right, our final subproblem will be what? When we reach this point, that will be the answer. Is this clear to everyone that when we are going from left to right, when we reach the end of the array, the answer that we have currently would be our final answer? And we're trying to, check for all possibilities here. So think about some state or think about some recursive idea. Let's say you don't have any DP idea in your mind. Think about some recursive idea. Let's say you are standing on this point, on the very first point. How many choices do you have for this point? You can either pick it up or you cannot pick it up. You have two choices. Okay. Let's say I pick it up. Let's say I pick this element up. So what will be my current sum if I pick up my element? I will just say that sum plus equal to, let's denote this array by a of 1 and 1 based indexing. Right? And can I now pick up this element? If I've picked up this element, can I now pick up the next element? So can I say that this subproblem, this problem that I'm standing here, will be dependent on this problem if I pick this element up? Right? Basically, when I'm picking up an element, I can only pick up an element now, which is like at least after leaving one element. We have left this element now when we have picked up this element. But if let's say I tell you that I'm not picking up this element, rejecting this element, then can I pick up the second element? Yes, we can, right? So tell me some state that comes to your mind. Tell me a sub problem that we can solve. Can I say that if I have an array like this, and let's say solve this problem till this point. Let's say I have already made my choices, and I have covered all these elements here. I have made my choices for these elements, and I'm standing here. So what do you think are the two possibilities for the element standing here? There are two possibilities. Either you can pick it up or you can not pick it up. Right? Okay. What I'm saying is that I've already processed this part of the array. This part of the array I don't even know about. I have already processed the prefix. Basically, I have decided on which elements I want to pick up and which elements I don't want to pick up. This is what I've done till this point, and I'm standing on the ith element. Okay. So if I were to look at the first possibility, which is that you pick up this element, let's say this was the array. Let's say you pick it up. What can you do now? Okay, somebody has written state is dp of I gives the maximum possible sum given in the condition up to the ith element. Good. This is a good dp state. And you've also written what it means. So I think you're learning. This is really great. But I mean, for people who are not able to understand, let's talk about this. Like, if we pick up this element, what happens? I have already processed all of these elements. So if I pick this element up, can I pick this element just to the left of it? Can I pick it up? Yes or no? No, right? So if let's say the first possibility is pick ith element. If I pick the ith element, now my answer is what? It will be first of all a of I, because I'm picking that element up, plus f of I minus 2. Because what? Because I've already processed this part of the array, right? And if I'm not picking it up, what happens then? Then my answer is nothing but we don't really care about this. So I just say that what is the maximum answer till this point? So I say f of I minus 1. This is not pick. Are these two things clear? Like, is this making sense? What is happening? Basically, you have an array, and you're standing at this point, and you have already processed this part of the array, and you know this value. Like for every index, you know this value, f of I, maximum sum possible till index I. Let's say this is something that you already know about. Like, you've processed the part from this part, from the starting to this point, and you have this value stored for every index. F of I meaning the maximum sum possible till this index I, following this condition that you do not pick up any two adjacent elements. Right? So how will I define my DP state? I can say DP of I is what? Let's have some, can I write text here as well? Okay, how do I like increase the size of this? Anyway, let's just, increase the size like this. So can I say that, let's have another page. Can I say DP of I is equal to maximum sum possible till index I, such that we are never picking up adjacent elements. Can I say this? DP of I. Right? So what do you think? Like, we have two possibilities, right? Pick the current element up, do not pick it up. So if you pick the current element up, what do you think will be DP of, like, DP of I will be A of I. Like, you add your current value, but then you say that you cannot pick up the just previous value. So you say DP of I minus 2. And in this case, what happens? You have DP of I being nothing but DP of I minus 1. Because now you don't really care whether, I mean, if you're not picking up your current element here, if you're not picking up your current element, this one, then you're free to pick up the last element, right? So is this concept clear? Like, is this problem clear? We have a state. This is the state. And this is the transition. Basically, we have two choices. But what do we want? We want the maximum out of these. So what should we do to find out the transition? Shouldn't we take the maximum of these two? Like these two possibilities that I have? So what I'll say is that dp of I is nothing but maximum of A of I plus dp of I minus 2, comma, dp of I minus 1. Is this clear to everyone? The state and the transition. Okay, so let's move to this next slide. And I'll tell you how you can, this is what we've discussed till this point. Like we've discussed this approach when we're representing the state with just one parameter. What is the parameter that we're using to represent our state here in this problem? What is the parameter? We have a state, but we need to have some parameter to differentiate between two states. I is the parameter, right? So how many parameters are we using to define a state here? We are using just a single parameter. In that matrix problem, we had two parameters, I comma j, right? So this is what we have discussed till this point. Like dp of ij, dp of I is nothing but like checking for both possibilities. The first possibility is that you pick up the current element. If you pick up the current element, then you cannot pick up the last element. So you say ARR of I, which is the element at the ith index in the array, plus dp of I minus 2. And if you leave the ith element, then you are free to pick up the last element as well. So then you say dp of I minus 1. And the final subproblem should be clear to you because how are we processing this array? We are processing this array from left to right. So where will our final answer lie? Our final answer will lie here, right? When we have processed everything. So this is basically like considering zero-based indexing, dp of n minus 1. If you consider one-based indexing, then dp of I will be the maximum sum from 1 to I. And then the final problem will be dp of n, the final answer. So is this concept clear to everyone, like this idea? Let's talk about one more idea on the same problem, representing the state using two parameters. Okay. Let's say I am on the ith element. I am standing on the ith element and I say that dp of I comma 0 is equal to maximum sum till index I such that you do not pick ith element. What do you think will happen here? Like this is dp of I comma 0, and similarly you have dp of I comma 1, the same thing, but when you pick the current element, pick the ith element. Is the state making sense? We have two states now. dp of I comma 0 signifying that you are processing the array from 0 to ith index such that you do not pick up the ith element. So I have signified this by dp of I comma 0. dp of I comma 1 means that you have processed your array from index 0 to index I, but you are also picking up the ith element. So how do you define the transition now? First of all, before you move to the transition, is the state clear? Are these two states clear? And do they seem valid to you? Or do you see any problem in these two states? I mean, is the definition of these two states clear to all of you? dp of I comma 0 means you go from index 0 to index I and you leave the ith element. dp of I comma 1 means you go from index 0 to index I, but you pick up the ith element. Was the 1D dp not enough? It was enough, but I think some people might have thought along this line as well. Like defining two different states for when you're picking up the ith element and when you're not picking up the ith element. So I thought of like sharing this as well. So how do you write dp of how do you write dp of I comma 0? What happens here? Here we are not picking up the ith element. So in the previous element, what do you have? You have two choices. You can either pick it up or you don't pick it up. So what you can do is you can define it like dp of I minus 1 comma 0. This is the case where you don't pick up the previous element. And then you have I minus 1 comma 1. This is the case where you pick up the ith element, pick up the I minus 1th element. Similarly, dp of I comma 1 will mean what? What will happen here? You will first of all pick up your current element, which will be ARR of I. But can you now pick up the previous element? If you have picked up the ith element, can you pick up the previous element? No, you cannot. So where will that answer be stored? It will be stored in answer of I minus 1 comma 0. Is this correct or not? When you have when you're not picking up the ith element, you can basically pick up the previous element or not pick it up. So you have two possibilities here. But when you're picking the ith element up, you cannot pick up the previous element. So you add your current value, and then you say that in the previous element, you don't pick it up. So first of all, tell me, do you think that this is like, is this useful? We are creating a 2D array instead of a 1D array. Is this better or is this worse than the previous approach? What do you think? Better or worse? This is actually worse because now you're using two parameters to define the same state, right? So is this idea clear that you can even solve this problem using two states? I mean, two parameters to define your state. So dp of I comma 0 maximum sum in 0 to I if we don't pick up the ith element. Dp of I comma 1 is maximum sum in 0 to I if we pick up the ith element, right? For the transition, it's like when you're not picking it up, you have two possibilities for the previous element. When you're picking up your ith element, you don't have a possibility or you don't have any choice in the previous element. And your final answer is like this time there are two choices. Is this part clear? That when you're defining your final answer, now you have two choices. When you reach the end, there could be two ways. Either you pick up the last element or you don't pick up the last element. So you consider the maximum of these two, right? So I hope this is clear to everyone. Okay. Now we're, I think, going to talk about just one more slide. Yeah, we have actually just two more slides, so we can talk about all of these concepts. Let's first of all talk about time and space complexity in DP. Read the slide once on your own and tell me if it is making sense to you already, even before we have talked about it. Right now, we haven't discussed the time and space complexity of the previous approaches, although we have a little bit, like we've discussed a little bit of these, but we haven't defined a formal way to find the time and space complexity in a DP problem. So this is actually the formal way to find the time and space complexity. But tell me whether this was not obvious. These two things. Was it obvious or was it not obvious? It was obvious. After a little thought, yes. Okay. So understand it this way. Whenever you have a state, first of all, let's say you have a problem, you have a very big problem. And now let's say you divide it into, let's say, 10 to the power 6 sub-problems. Okay. Let's say you have a very big problem, you divide it into 10 to the power 6 sub-problems. And the answer of every sub-problem can be found in just 5 steps. The answer of every problem can be found in 5 steps. So how many steps do you need in total to find your total problem, like to solve the final problem? 5 into 10 to the power 6, right? So that's exactly how the time complexity is working out here. You have a very big problem. You break it down into smaller sub-problems. What are the sub-problems called? What do you call a sub-problem in a formal way in DP? You have a very big problem. You divide it into smaller sub-problems, but there is a name for it. It's called a state, right? So the number of sub-problems, basically the time complexity is the number of sub-problems into time to calculate one of them. Is this clear or not? You have a very big problem. You divide it into chunks. Now, every smaller chunk can be found in, let's say, 5 steps. So the total steps that you're going to take is like n into 5, n being the number of subproblems. Okay, now let me give you another example. Let's say you have n states. To find f of n, you need n steps. And sorry, not n steps. Basically, how should I put it? Okay, let's say you have to find f of 2, and to find f of 2 you need n by 2 steps. Okay, n is some very big number. To find f of 3 you need n by 3 steps. To find f of 4 you need n by 4 steps. So tell me one thing, wouldn't it be the average time to calculate one subproblem? So that is exactly what I'm going to be discussing right now. What I'm telling you is that operations to evaluate it. To find f of n, you require n by 2 operations. Sorry, not f of n, but f of 2. To find f of 2, you require n by 2 operations. To find f of 3, you require n by 3 operations. So now tell me, if I have to find f of 1, I have to find f of 2, I have to find f of 3, so on. And I have to find f of n at the end. We have n smaller problems, and to find this subproblem, you need n by 1 step. To find this problem, you need n by 2 steps. To find this problem, you need n by 3 steps, and so on up till n by n steps. So now can I use that same formula that I told you guys? The number of states into the transition time for every state. Can I use that now? Because now the transition time is not same for every state. So the actual formula, the actual estimate for the time complexity is nothing but the summation of transition time. Sum of transition time. Okay. So this should be clear now. So basically for this type of a problem, when you have n steps, then n by 2 steps, then n by 3 steps, at the end it becomes n by n. The answer is n log n. Like there is an estimate, you can read about it, you can Google it up, and the number of steps here are actually n log n. So to a very naive person, this might seem as order of n square. Because for this first state, we are using n steps. For the second state, we are using n by 2 steps. For the third state, we are using n by 3 steps. So somebody might say that this is nothing but n square operation. But it is actually order of n log n. Okay. So I hope this is clear. Like the estimate is the number of states into transition time for each state. But if you know that the transition time is different for all the states, you just take the summation of all the transition times, and that will be the time complexity. Fine. Now, the space complexity is very simple. You define the number of states, and then for every state, you define how much space is required for that particular state. And that would be the space complexity. Right? So is this clear to everyone? Time and space complexity in a DP problem? Okay, let's see how much more do we have. So we have 2 more slides. We have this recursive versus iterative DP, and we also have this one more special thing that I wanted to cover, which is like general technique to solve any DP problem. I think what we can do is we can, cover these 2 things in the next class, because we already discussed a lot, and I don't want to, make it like really overwhelming for a lot of you. So I think it would be better to discuss these 2 slides in the next class. But everything that I've discussed till this point, is that clear to you guys? Or do you guys have any doubts on that? So somebody is saying we also have a stack space, right? In recursion, right? That's right. So we'll be talking about this, when we discuss the slide, recursive versus iterative DP. And then you will realize that the space complexity of an iterative solution is much better than that of a recursive solution. Right? So, but I think it would get really overwhelming if I put a lot of concepts just in one class, in the very first class itself. So let's discuss these 2 concepts in the next class. Okay. And this concept is going to be really interesting, a general technique to solve any DP problem. So after this slide, you will not have to memorize any state. You will not have to memorize any transition. you will have a toolkit with which you can solve any DP problem in the world, right? All you have to do is like apply your brain there, but you'll have a way. You'll have a very strategic way to find the answer for any DP problem. Fine. So I think we can wrap it up now. Any doubts? We can spend 5 more minutes taking doubts. But yeah, this was what I had for today. And let me mark it here. Sometimes it's difficult to recognize that the problem is a DP problem. That is also what I'll be discussing. Don't worry about this. So probably in the second or probably in the third class, I will be talking about this concept of identifying a DP problem. Okay. So when I tell you that this is like a 7-lecture series where I will be discussing a lot of stuff, just assume that after these 7 lectures, you will be in a very good position to first of all identify whether a problem is a DP problem or not. You will have a very formal, very strategic toolkit with you, with which you can solve any DP problem. And also, you will not be like memorizing anything after this point. How to turn top-down memorization into bottom-up? So this question that you have asked, I would like to first of all tell you that these terms like top-down, bottom-up, these are some terms that have been made up by people. You don't have to worry about these terms. When I give you a general toolkit, these terms will never come into the picture. Defining something like a top-down DB or a bottom-up DB, I don't think it makes sense. This confuses everyone. So if you have a general technique to solve any DP problem, these terms will not come into the picture. Whatever terms will come into the picture, I'll tell you that. Okay. So don't think about this. How to convert a top-down DP into a bottom-up DP? This is not relevant. This will not help you to solve a DP problem. It will only confuse you. Right. So somebody's asking, will we get the recording? Yes, we'll get the recording.